So welcome to this second part of this problem, Arrhenius equations. So here we'll see a reaction proceeds 5 times more at 60 degrees centigrade as it does at 30 degrees centigrade. Estimate the energy of activation. So here so the activity is given 60 degree and here 30 degrees. So we'll use this value. So rate of it is second rate is given here. 2 rate is a rate of 2, that is 60 by 30. You can see this one. So again by rate 1 will be equal to K2 by K1. So again rate 2 by rate 1, that is equal to how much is there. So again we have used the formula. Rate is proportional to concentration K into reactant to the product N. So from this we can get value. So K2 by K1, so here rate 2 by is 5 times, so we can write here this is the R2 by R1 is equal to 5. So here reaction proceed 5 times the more 60 degrees, so definitely this is equal to K2 by K1 is equal to 5. So use this value, logarithm value of activation of this one rate constant, that is log of K2 by K1 is equal to EA by R, and here temperature not R, this lower temperature minus higher temperature. So K2 by K1 is 5, you can put this value over here. So this is 2.303 log of 5, and EA is given. E we need to find out EA is equal to, and R is given here, that is, so in terms if you want to find calorie, write here 2 into 10 to the power minus 3, so this will be your in kilocalorie. So here divide it, 1 by temperature is lower temperature, that is 303 minus higher temperature 333. So why 3? Because this is 60 degree and this is 30 degree centigrade, this is 60 degree centigrade. So here activation energy will be equal to, on solving, 10.757 kilocalorie per mole. So this is our basically answer. The rate constant of a reaction increases by 7% when its temperature is raised from 300 Kelvin to 310 Kelvin. While its equilibrium constant increases by 3%. So here equilibrium constant increases 3%, but here rate constant is increased by 7%. So for first at 300 Kelvin, rate constant is how much? That is K. This is rate constant. So again rate constant at 310 Kelvin will be increased by 7%. So we can write here K into 7 by 100 into K. So this will becomes 1.07 into K. So now we have to find the activation energy of this one. So activation energy will be 2.303 log of this is K2 by K1, and this will be your forward reaction, that is activation energy for this reaction, because backward reaction 3% they have given here. So this is forward reaction, so this is divided by calorie, and temperature is again to temperature given 1 by 300 minus 1 by 310. Okay, so K2 by K1 will be how much? It is nothing but the 1.0.7 by K. This is given here. So we can say here K at 310 by K at 300 is equal to here your 1.07. So we can put this value over here. So on putting 3.07 log of 1.07, so here EA by 2, so here 1 by 300 minus 310. So on this solving we will get here EA of this one reaction, it will be how much? 1258.68 calories. So we got this much value. Now at equilibrium, constant at 300 Kelvin is how much? The equilibrium constant increases by 3%. Okay, so here we have to find the new equilibrium constant over here. So now we can see equilibrium constant at 300 Kelvin is, so this will be some new constant K. Okay, so this is increases how much? 3%. So you can write here K dash plus K at 310 Kelvin will be your K dash plus 3 by 100 into K dash. So this will be nothing but the 1.3 K does. Okay, so again we can see here this is K at 300. In this case, this is the case 1, you can see here, and this is your case 2. So now here K 300 by K 300 will be equal to 1.03. So again we will take the same equation. So again 2.303 log of K2 by K1 is equal to, here we can see here delta H by R, and temperature is again same, that is 300 minus 1 by 310. So if we solve it, so on solving we will get answer here. So here delta H by, this is your 2, and this is again solve it, 0.303 log of 1.03, and this is equal to 1 by 300 minus 1 by 310. So on solving you will get here delta H is equal to 549.89 calorie. Okay, so this is for the equilibrium constant delta heat of energy of this one. So we have to find the activation energy for the reverse reaction. So forward is, you know that total delta H, also know that. So we can write here delta H is equal to activation energy for forward minus activation energy of backward. So we need to find the activation energy of the backward. So total is given how much? So it is 549.89. So this will be your how much? So forward reaction is given here, this is backward reaction. So if you put this side, so this will becomes how much? So minus, this will be plus 158.68. so you will get value here 708.79, that is calorie. So this is our basically answer. Given out the temperature coefficient for the saponification of ethyl acetate by sodium hydroxide is 1.75. so calculate the activation energy. So again we will use here K2 by K1, that is temperature coefficient. They have given how much? 1.75. So now we need to find out the EA. So again you use the Arrhenius equation, 2.303 log of K2 by K1, and this is equal to EA by R, and temperature is lower temperature minus higher temperature. So what is the lower temperature, what is the higher temperature? So again in this case, so again here, so again here temperature not given here, so this hint is given here, temperature coefficient. So we can write here temperature coefficient is nothing, coefficient is the ratio of rate constant, is the ratio of rate constant at 35 degree centigrade and 25 degree centigrade. So this is the ratio over. So this we have to remember, this is the ratio of this one. So we know this temperature, that is T1 and T2. So we can put that here value. So we can put here 2.303 log of 1.75 and EA. So EA we need to find out, and R is given here 1.987, and temperature again it is 298 minus 308. So now we can solve this value. So if you take this value EA, so on solving you will get here 10.27 kilocalorie per mole. So mathematics, I hope that you know very well. So you will get this answer. A given sample of milk turns sour at room temperature 20 centigrade in 64 hours. So in a refrigerator at 3 degrees centigrade, milk can be stored 3 times as long before it sours. Estimate the activation energy for souring of milk, and second is the how long it take milk to sour at 40 degrees centigrade. So here it is very clear. So one is 3 degrees centigrade, one is 40 degrees centigrade. So here it is 3 times more. So first, in this case, first we need to find out the activation energy. So from that activation energy we will just find out the time, that is the how long it will take. So first we need to find out the activation energy. So here two temperature given, that 293 and this is here 276. So in this case you will get this two temperature. Just take the first value 2.303. here activation energy 2.3 log of, so K is given here, higher temperature is 20 degrees centigrade. So K2 is 293. So here 293 put here, and here we need 276 per 3 degree centigrade. So again activation energy divided by R. So R is here 2. So here you take 1 by T1. T1 is nothing but the lower temperature minus higher 293. So on solving you will get here activation energy is 10453.95, or we can say 10.454. This is your kilo Kelvin. So we got the activation energy. Now second case is that how long it will take to sour the milk at 40 degrees centigrade. So once you know that this one K, so we can find out the this temperature K. So K3 by K2 depends on the time. So here we can write here 2.303. so log of K3 by 2. So K3 means this one, second is 40 degree centigrade, and second is your 40 degree. We have to find out how long it will start 40 degree. So 20 to 40 degree centigrade. So 20 to 40. So it will be your temperature will be your 313 divided by K is your 293. So 20 to 40. So again here EA we know that is nothing but the 10.454, and again divide by 2. So divide by 1 by 293 minus 1 by 313. So on solving we will get this value. So K 313 by K 293, we solve it, you will get here 3.12. This is nothing but the time taken by the second. This is 2, that is the second case. Second case means 293 by time taken at 313 Kelvin. Why? Because the rate constant is inversely proportional to time, and we know the value from the half-life, that is the K, the time is inversely proportional to K. So if milk is not soured up to 64 hours at 20 degree centigrade, it will not sour up to 192 hours at 3 degree centigrade. Means what? At 64 hours at 20 degree centigrade, 20 degree centigrade milk is not sour. So if you take 122 hours also at 3 degree centigrade, it will not sour. So we can write here temperature at 313 divided by temperature at how much, 293 is equal to how much. So temperature at 293 divided by K at 313. So we can write here second case, that is 64 hours given here. So we can write here 64 multiplied by 1 by 3.12. So 3.12 means 330 by this range. So we will get this temperature, that is equal to nothing but the temperature at 313 Kelvin. So on solving, 313 Kelvin will be 20.5 hours. So this is our value. The rate constant for the first order decomposition of a certain reaction is given by the equation log K, some second is given here, natural log 1434 minus 1.25 into 10 power 4a. So we have to find the activation energy. 3 is given, rate constant, and at what temperature, half-life period be 256 minutes. Okay. So first we have to find the ES. ES again we can compare with this one. So log of K is equal to, this is we can compare natural log of A for A equation minus EA by, that is T is given here, RT. So this is, so here we can compare. So EA by RT is nothing but the 1.25 10 power 4 by divided by 2. So we can write here EA by R is equal to how much, 1.25 into 10 to the power 4. So R value we know that very well. So here we can write here EA is equal to 1.25 into 10 to the 4 into 1.987. So here you will get the value, that is 24.83 kilocalorie per mole. So this we got the value. So A is over. Now come to B part. So natural log of K is equal to 14.34 minus 1.25 into 10 to the power 4 divided by 500. So why 500? Because temperature is given here 500 Kelvin. So again we can solve it. So on solving, K will be get 2.35 into 10 to the power minus 5 seconds. So we got this answer. Now C part. So here half life they are asking, so K is equal to 6.93 and this divided by 256 into 60. So now we can use natural log of 0.693 divided by 256 into 60 equal to 14.34 minus 1.25 into 10 to the power 4 divided by T. So on solving here you will get T is equal to 513 Kelvin. So in this way you will get these answers. The energy of activation and a specific rate constant for a first order reaction at 25 degrees centigrade, that is 2 molecules of NTO and N2O5 will give you 2 molecules of NTO4 and oxygens are 100 kJ per mole and 3.46 into 10 to the power minus 5 per second respectively. So determine the temperature at which the half-life of the reaction is 2 hours. So you have to find those temperature in which the half-life reaction is made. So first we will find the this one K value they have given here. So we have to find the one second value, that is K2 value, because after 2 hours what will be the K2 value. So first K2 value will be, so for this half-life will be how much? So first K2 value is 6.932 and divided by time is given here, that is 2 hours. So 2 into 60 into 60. So you will get answer 9.62 into 10 to the power minus 5 per second. So you will get this one. Now for temperature, again you can use this one Arrhenius equations. So again log of K2 by K1 is equal to E by 2.303 into R, and there are two temperatures already given here. So temperature is 125 degrees centigrade and other temperature that we don't know. So other temperature is, so we can write here, so one is your 298 minus one temperature is your T2 temperature. So again they have given E also given and this also given, so we can use finally we can write like this is, so log of K2 is given, what is K2? 9.62 into 10 to the power minus 5, and what is K1? So K1 you can see here from here, so K1 is 3.46 into 10 to the power minus 5, and here EA is also given, so EA is that is 100 kilojoules, so 100 multiplied by 3 and here divided by 2.303 into R. So R is given 8.314 and temperature is 1298 minus 1 by T2. So on solving, now we can solve it, every value is given, so on solving T2 will be your 310 Kelvin. So this is our answer. Basically I am giving the idea how to solve a problem. So once you know this method, so you can easily solve a problem. What is the activation energy of a reaction if its rate doubles when the temperature is from 290 to 300 Kelvin? So we have to find the activation energy, rate is doubled. So it is very easy question. You use this value, log of K2 by K1 equal to E divided by 2.303 R, and here will be your 1 by T1 minus 1 by T2. So here rate is double, so you can write here log of 2 and EA we need to find out. So EA divided by 2.303 into 2 and temperature we can write here a lower temperature 290 minus 1 by 300. So definitely here you will get E is equal to 12062 calories, or we can say 1200 kilocalories. So this is our activation energy. So this question is very easy, you can easily solve it.